Previously, we have presented the flow rule for the case without hardening. However, plasticity in metals, they have a hardening behavior. This is the case without hardening, where once the stress reaches the yield strength, it remains at the same level at sigma 0. In reality, what could happen is that the stress level keeps on rising, so the material is sustaining higher the level of stress beyond the initial yield stress. And in the case of isotropic hardening, it means that if we were to unload and then reverse it, the loading, we could go beyond the initial yield strength in compression and reach the same level of stress as we've reached in tension. If we keep on loading it hard, still the compressive stress will keep on increasing, and we have associated also the plastic deformation. On the contour plot, it basically means that even though we are loading at this point, the entire yield surface is enlarging uniformly in all directions. So this is the meaning of isotropic hardening. Mathematically, it means that now our yield criteria is a function of both our stress and some hardening parameter, K. This hardening parameter is a representation of the accumulated plastic flow. As you can see here, our so-called current yield strength is increasing with respect to our plastic deformation. So K is a measure of the accumulated plastic flow. In the case of Vomises, this would mean that now we have a Vomises stress minus some yield stress depending on this K. In order to calculate K, we need to first evaluate K dot, the time derivative of K. And the popular choice is this work hardening expression of K dot. Here, tau dot product with the plastic strain rate gives us the power done by stress and plastic strain rate. And we divide this power by Vomises stress gives us an effective measure of plastic strain rate. So basically, K dot and Vomises stress, they are power conjugates. So for metals, for Vomises, we turn out this K dot is simply the same as lambda dot, our plastic multiplier. And to get the K, which is then relevant to our yield condition, we integrate the K dot over time along the loading path. So this is isotropic hardening. Basically, as K increases, our yield envelope is enlarging. There is a different hardening behavior, which is called kinematic hardening. This is a case where when we reach the initial yield strength, we have the hardening. Our stress keeps on increasing beyond the level of sigma 0, and then when we reverse the loading direction, we reach yielding before the original yield strength. So this is a shift. This shift is the same amount as this increase of yield strength. This has been observed in metal as a Bollinger effect. So when we initially load a bar in tension and beyond this yield strength, and when we reverse it, the yield strength become less. And in terms of the yield contour, the yield surface, it means that now the whole surface is not changing in shape or area, but is shifting along your loading direction. Mathematically, it means that now our yield criteria is applying on the shifted stress. So our Cauchy stress is shifted by alpha, which is so-called back stress. And this back stress is increasing at the same rate proportionally to lambda dot, our plastic multiplier. So this is an experimental observation. And so the rate of back stress is proportional to lambda dot, and multiply with a tensor function. So this is a lambda dot is scalar, and this function is a function of tau, our current stress level, and alpha, the current back stress. So this needs to be determined experimentally, the expression of HK. In general, we could have a combination of both isotropic and kinematic hardening. Then we would have the non-isotropic enlargement of our yield surface, and our yield condition contains both the back stress and our hardening parameter, scalar hardening parameter K. So they are both proportional to lambda dot, our plastic multiplier. In implementation, we can group K and alpha together as an array of hardening parameters. We call it capital K. Capital K contains both our scalar K and alpha, and then we can form a function H which relates K dot with a lambda dot, and this needs to be determined experimentally. And H is a function, generally a function of tau, the Cauchy stress tensor, and K, the current values of these hardening parameters.